Artificial Intelligence Course for Beginner by Knowledge and Information. In this video we are discussing about Part 4. Machine Learning. What is machine learning? Part 1. Machine learning is a subfield of artificial intelligence, AI, that focuses on the development of algorithms and models that enable computers to learn and make predictions or decisions without being explicitly programmed. It is a data-driven approach where machines are trained to recognize patterns, extract insights, and make predictions or take actions based on input data. In traditional programming, humans explicitly write code to instruct computers on how to perform specific tasks. In machine learning, instead of programming explicit rules, the computer learns from data and examples. The process involves training a machine learning model on a labeled dataset, where the model learns to recognize patterns and relationships between input variables, features, and the corresponding output, label or target variable. The machine learning model is trained through an iterative process that involves feeding it labeled examples and adjusting its internal parameters to minimize the error or difference between predicted outputs and the true labels. Once trained, the model can make predictions or decisions on new, unseen data by applying the learned patterns and relationships. Machine learning techniques can be broadly categorized into three types. 1. Supervised learning. In supervised learning, the training dataset consists of input-output pairs, where the desired output is known. The model learns to generalize from the labeled examples and can then predict the output for new, unseen inputs. Examples of supervised learning algorithms include linear regression, logistic regression, support vector machines, and neural networks. 2. Unsupervised learning. In unsupervised learning, the training dataset consists of input data without any corresponding labels or targets. The model's task is to find patterns, structure, or relationships in the data. Clustering algorithms, such as k-means clustering and hierarchical clustering, and dimensionality reduction techniques, such as principal component analysis, PCA, and T-distributed stochastic neighbor embedding, TSNE, are common examples of unsupervised learning. 3. Reinforcement learning. Reinforcement learning involves training an agent to interact with an environment and learn optimal actions based on rewards and punishments. The agent explores the environment, takes actions, receives feedback, rewards or penalties, and adjusts its actions to maximize long-term rewards. Reinforcement learning has been successful in applications such as game playing, robotics, and autonomous systems. Machine learning has numerous applications across various domains, including image and speech recognition, natural language processing, recommendation systems, fraud detection, healthcare diagnostics, financial forecasting, and autonomous vehicles. It enables computers to learn from data, adapt to changing conditions, and make predictions or decisions based on patterns and insights. Machine learning algorithms can employ various techniques to learn from data, including 1. Feature extraction. Feature extraction involves identifying and selecting relevant features from the input data that are most informative for the learning task. This process can involve techniques like dimensionality reduction, where the high-dimensional input data is transformed into a lower-dimensional representation while preserving important information. Feature extraction helps to improve the efficiency and effectiveness of learning algorithms by reducing the complexity and noise in the data. 2. Model evaluation and selection. Once the model is trained on the training dataset, it needs to be evaluated on a separate validation or test dataset to assess its performance. Various evaluation metrics, such as accuracy, precision, recall, and F1 score, can be used to measure the model's predictive accuracy. Based on the evaluation results, different models or hyperparameters can be compared and selected to find the best performing one for the given task. 3. Regularization and hyperparameter tuning. Regularization techniques are used to prevent overfitting, which occurs when a model becomes too complex and learns the training data's noise or outliers instead of the underlying patterns. Regularization methods impose constraints on the model's parameters to control its complexity. Hyperparameters, on the other hand, are settings that are not learned from the data but need to be manually set before training the model. Tuning these hyperparameters, such as learning rate, regularization strength, or network architecture, can significantly impact the model's performance. 4. Online and batch learning. Machine learning can be performed in different modes, depending on the availability and nature of the data. Batch learning involves training the model on the entire dataset at once. This approach works well when all the data is available upfront, but it may not be feasible for scenarios with continuous data streams. Online learning, also known as incremental learning, allows the model to update its parameters continuously as new data arrives. This is particularly useful in dynamic environments where the model needs to adapt to changes over time. 5. Transfer learning. Transfer learning involves leveraging knowledge gained from one task or domain to improve performance on another related task or domain. Instead of starting from scratch, a pre-trained model on a large dataset can be fine-tuned or used as a feature extractor for a different but related task with limited labeled data. Transfer learning helps to overcome the challenge of limited data availability in specific domains and accelerates the learning process. Machine learning is a rapidly evolving field with ongoing research and advancements. The success of machine learning algorithms relies on various factors, including the quality and quantity of the training data, the choice of appropriate learning algorithms, the selection of relevant features, and the fine-tuning of hyperparameters. The application of machine learning has the potential to revolutionize industries, enable automation, and drive innovation across a wide range of fields. Here are some additional key concepts and components related to machine learning. 1. Feature engineering. Feature engineering is the process of selecting, transforming, and creating input features that are most relevant and informative for a machine learning task. It involves understanding the domain and the data, identifying meaningful attributes, and creating representations that capture the underlying patterns and relationships. Effective feature engineering can significantly impact the performance of a machine learning model. 2. Cross-validation. Cross-validation is a technique used to assess the performance and generalization ability of a machine learning model. It involves splitting the available data into multiple subsets, typically a training set and a validation set. The model is trained on the training set and evaluated on the validation set. Cross-validation helps to estimate the model's performance on unseen data and detect potential issues like overfitting. 3. Bias and variance trade-off. In machine learning, the bias-variance trade-off refers to the relationship between a model's ability to capture the underlying patterns, bias, and its sensitivity to variations in the data, variance. A model with high bias may oversimplify the relationships in the data, leading to underfitting. On the other hand, a model with high variance may capture noise or irrelevant details, leading to overfitting. Achieving the right balance is crucial for model performance. 4. Model evaluation metrics. Model evaluation metrics are used to quantify the performance of a machine learning model. The choice of metric depends on the specific task and the nature of the problem. For example, in classification tasks, metrics like accuracy, precision, recall, and F1 score are commonly used. In regression tasks, metrics like mean squared error, MSE, root mean squared error, RMSE, and R-squared are often used. The selection of appropriate evaluation metrics is important to assess how well the model is performing. 5. Deployment and monitoring. After training and evaluating a machine learning model, it can be deployed to make predictions or decisions in real-world applications. Deployment involves integrating the model into a production environment where it can receive input data, perform predictions, and provide outputs. It is important to monitor the model's performance over time, retrain it periodically with new data, and ensure that it continues to deliver accurate and reliable results. 6. Ethical considerations. Machine learning models can inherit biases present in the data they are trained on, which can lead to unfair or discriminatory outcomes. Ethical considerations are becoming increasingly important in machine learning to ensure fairness, transparency, and accountability. It involves addressing issues like data privacy, algorithmic bias, interpretability, and responsible use of AI systems. In next video, we will discuss about what is machine learning, part 2. Thanks for watching. Please like, share and subscribe.